So let's look now at this picture on the left. So we have a purple plane rigid body rotating about a fixed axis. And we're going to use our right hand rule, and that's going to determine our positive and negative direction. And let's start defining some of the things we have here. So we have our point O, and that's just, the point at which we're rotating about. And we have a line R, and that's going out to a point P. And P can be, on any point of this plane rigid body, it's going to have a circular motion, no matter where it is. So here we have it drawn right on the edge, but no matter where you draw it, it's always going to have circular motion. So we're going to be talking now about angular motion for these types of problems. And we can say that lines and bodies only are going to have angular motion. So our particles will not, but in a case like what's shown here, this is going to be falling under that category. And important to note that all angular motion doesn't need an axis about which to rotate, but in here we do have a fixed axis. So at this instant, the angular position of R, we can write that as our angle theta. And this is going to be measured from our fixed reference. So we can say theta, and it's going to be a function of time. So our angular displacement, therefore, is going to be defined as d theta. So that's going to be our change in angular position. So now, like we've done many times before, we're going to say that our angular velocity is going to be the derivative with respect to time of theta. And we could write that as theta dot. But going forward, we're going to use omega to designate our angular velocity. And of course, we can say angular acceleration, we can write as d2 theta over dt squared, or theta double dot, but we're going to say, going forward, alpha is going to be designating our angular acceleration. Now, another important thing to note is that any line on the body is going to have the same angular velocity and acceleration. And we also can say that our alpha here is equal to omega d omega over theta. That's just another way that we can define alpha. Now, if alpha equals a constant, we can use a certain set of equations. So we could say, and these should look pretty familiar. And another important thing to note is that these problems are really set up ideally for polar coordinates. So that's kind of where we're going to be drawing from, as you're going to see in a moment. So here are a set of equations that we can use when we have a constant acceleration. So now you can see here we've drawn another sketch on to the right, and this is as if we're looking down on this plane rigid body. So, our axis would be pointing up at us, and we've pretty much drawn the same situation that we have on the left. So what happens now if we want to find the velocity of this point P? So again, we know that any point that's rotating about a fixed axis is going to have a circular path of motion. So we know that P is going to be moving in a circle. So we can say that our velocity is going to be perpendicular to this line R, and we'll call it VP, and it's going to be tangent to our path of motion. So we can write an expression for VP, and we can say VP is going to be equal to R times omega times U sub theta. And we derive this because we can say VP equals R dot UR plus R theta dot U theta, and this is going to become 0 because R is going to be a constant. So VP is going to end up being equal to R theta dot U theta, and as we just defined, theta dot is going to be R omega. So here is our VP expression, and if we want to say, the magnitude VP, we're going to write that as omega times R. So now if we want to write our acceleration of point P, we can say AP equals R double dot minus R theta dot squared UR. And again, this is just, what we know from our polar coordinates from our previous lectures. So times 2 U sub theta. And again, with R being constant, this is going to be equal to 0. And this is going to be equal to 0. So let's write this out again. This is going to be equal to negative R theta dot U sub R plus R theta double dot U sub theta. So our final expression for the acceleration of point P, we can write that as negative R omega squared times U sub R. So that's our R component, plus our theta component is going to be equal to alpha times R. So that is our final expression for our acceleration at point P. So here in our top right, we've drawn in our R and our theta component of our acceleration, and we have created in green our resultant vector, so a sub p, which is going to be expressed by our equation in yellow that we just defined. So now if we look in our bottom left, we have essentially the same picture, but we're going to look at it from another angle. And we're going to define all of these values using vectors. So we could write v sub p as equal to the cross product of omega and R, like so. And as you can see on our picture, we have omega is pointing up in the same direction of our axis, and we have essentially all the same components as we did before. So this is going to be how we write as vectors omega cross R. And for our acceleration, we can say this will be equal to alpha cross R plus omega cross R, or we could write it a little simpler as a sub p equals alpha cross R minus omega squared R. Thank you for watching. If you like this video, please be sure to give it a thumbs up and subscribe. That really helps support my channel and helps me continue making videos for you guys. I'll see you next time.